So we have two things in physics. We have the electric field and the electric potential with respect to infinity due to a point charge. And so suppose you have something like a dipole like this, and you want to find the electric field. There's actually two ways you could do that. Number one, I could take a point and find the electric field due to this charge, which would be that way, and then the electric field due to this charge as a vector, it would be this way. And then the sum would be the vector, the electric field would be the vector sum of those two electric fields right there. Okay, so that's not super trivial because these are not at easy positions, and so you have to find the vectors and find the angles and all that stuff. I mean, it's not impossible, and we're going to do it. Okay, but there is another way to do it. Suppose I want to find the electric field down here. What if I want to find the electric potential? Oh, and I should say the electric field due to a point charge is 1 over 4 pi epsilon naught q over r squared r hat. So in this expression, r is the vector from the point charge to where you want to find the electric field, and r hat is a unit vector in that direction. So this is a vector equation, and it's important to use that. But it is a vector, right? So you got to find r, you got to find r hat, blah, 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 and it's a lot of work. What if I want, and then I could do the same thing over here. It's possible to find the electric potential right here. The electric potential is a scalar value. And so the electric potential due to a point charge with respect to infinity, saying the potential at infinity is 0, because it's always really a change in potential, is 1 over 4 pi epsilon naught q over r. You don't have to find the direction. So when I find the potential due to this one plus the potential due to that one, it doesn't matter about the direction. I just find the distances. So it's a little bit easier. So it's easier to find the potential than the electric field because it's a scalar. But could I use the potential to then find the electric field? Well, in 3 dimensions, we have the following relationship between the electric field and the electric potential. The electric field is equal to negative del V. And this is the del operator. Some people call it something else. I'm going to call it del. And it looks like this. It's a vector operator. In Cartesian coordinates, it looks like the partial, let's write it like this, x hat times the partial with respect to x, plus, this is a gradient too, you can consider this, plus y hat, the partial with respect to y, plus z hat, partial with respect to z. So it turns a scalar value into a vector and says how much does this change in the x direction? That's my x component. How much does this change in the y direction? That's my y component. How much does this change in the z direction? That's my z component. So what I want to do is to create a dipole, find the electric field at some point, and I can check my off-axis point with these two approximate formulas for the far field approximation of a dipole. And I have videos over this derivation. If you want them, I'll show them to you. If you're on this axis and your distance r, this is the distance right here, r from the center, then the magnitude electric field is 1 over 4 pi epsilon naught, which is a constant, 2qs, with q is a charge on one of these, and s is their separation, over r cubed. So I can actually build a model for the electric field. I can check it with this. I can check on the perpendicular axis, which is right here. Same value, but it doesn't have the 2. And then I can find the electric field anywhere, numerically. I can find the electric potential anywhere. But here's what I want to do. I want to do this. I want to do this numerically. Okay, so if this is in just the xy direction, then there's no change in z, so I don't have to worry about that. But now what if I pick some point over here and I see how does the potential change in the x direction? That's literally what this says. So if I look at a plot of potential as a function of x around that point, the slope of the line, which would be tell me how it changes in the x, is the partial derivative. And then I can do the same thing over here. So I can find the potential at this function, at that point, and then just vary it back and forth. And then I can check it with my other expression. So the first thing I'm going to do, I'm going to make a dipole. I'm not going to make a visual of it because I don't really need that. I'm going to make a function to calculate the electric field. I'm going to make a function to make the electric potential, and then I'm going to check that with this. And then I'm going to pick a point and make these two graphs, and then use that to calculate the electric field based on the potential and compare that to this electric field. I know that's a lot of stuff, and we're going to do it in Python. I'm going to do it in Python. I'm going to give you the code. So let's just get started, because everyone wants to start. Okay. So go over here. Okay, here I am using Trinket VPython, GlowScript VPython, in Trinket. I'm sorry, I'm using GlowScript Web VPython, and this is in Trinket just because it makes it a little bit easier that way. So let's just make up our dipole, and I didn't even think to make a value yet. So I'm gonna say k equals 9 times 10 to the 9th. This is my 1/4 pi epsilon naught. It comes up all the time. Now I need my q. Let's say it's 5 minus and plus 5 nanocoulombs. The number doesn't really matter. 5 e negative 9, and my separation distance is going to be I'm thinking big here. Let's say a millimeter, 0.001 meters. Okay, so I'm going to go ahead and I've calculated the electric field due to a dipole before. I'm going to go ahead and this is centered at the origin. So with that, I can say, let's just go ahead and make let's just make this a whole thing a function. Def E. I'm just going to call it E, and I'm going to give it a value of RO, my observation location. Where do I want to find the electric field? This is going to return that. So that way I can just say E vector, done. So let's indent this. Yeah, I'm putting the dipole in the function, which you don't have to do. You can put it out, but that's fine. Okay, so let's call this Q, let's call RQ1. RQ1 is the vector location of charge 1. So that's going to be, if I put the positive on the right side, this is going to be equal to vector s over 2, 0, 0, right? Because if I shift over half of that distance s, that's where that's going to be. And then RQ2 is the negative one. It's going to be vector negative s over 2, 0, 0. 0, 0. Okay. I know I have positive and negative. Now, and I know my observation location. So let's find R1. R1 is the vector from RQ1 to RO. So I'm going to say R1 equals RO, which I passed into the function from when I defined it, minus RQ1. And then R2 is going to be RO minus RQ2. Okay, so now I have the two R's. I can calculate, let's just calculate the electric field all in one fell swoop. So it's going to be ET, that's a temporary, I'm just going to write it out. It's going to be K times the positive charge, Q, times norm R1. That's that R1 hat. That's the unit vector from the positive charge to the observation location. I need to divide that by the magnitude of R1 squared. And then I need to do the same thing for the negative charge, but it's negative. So it's going to be negative K times Q times norm R2 divided by mag R2 squared. And that's my electric field, and I'm going to return that. Return ET. And let's just test it. Okay, so I'm going to say print E equals, let's do it on the x-axis at a vector. So I'm going to say E, I'm going to put the vector, it says 0.0100, so that's 1 centimeter away. And that's the electric field, so I'll say the units, newtons per coulomb. And let's run that. I'm looking for an error, which I have. Okay, good job. Can't find variable RO. Why can't it find RO? R0. Oh, I did it again. Okay. So there's the electric field. I don't know if that's right, because I can't just... Okay, so we can test that, though. So let's just say E far field is going to be K times 2 times... Ooh, I did do this. Let's put this up here. Let's put that outside of the function. 2 times q times s divided by 0.01 cubed. And I just, because that's r, right? And then print E far field is going to be equal to E far field newtons per coulomb. So these may not be exactly the same because that's a far field approximation, but they should be close. Okay. I think it's working. Okay, so I'm happy with that. Okay, so that's my function for the electric field, and I need that to check, but now I need to calculate a function for the potential. So I can say def v RO, and it's going to be very similar. I'm going to have the same stuff, right? Oh, this? Yeah, that's fine. This, I need this too. I need all that stuff. But that should not be double tab indented. So I have R1 and R2 are the vectors from each charge to the observation location. So I'm going to say VT, the temporary potential, is going to be K times Q divided by mag R1 minus K times Q divided by mag R2. And that's it. And then return VT. Okay, and I'm just going to assume that works. So now what I want to do is I want to pick a point. So let's say R pick, RTO for temporary. It's going to be the vector. I'm going to pick it off the axis. So let's say vector 0.01, 0.02, 0. That's where I want to find the electric field. But the first thing I'm going to do is to make a plot. I should save this. Finding dipole E from V. So the first thing I want to do is plot the potential as a function of x position around that region. Okay, so I'm going to make a graph. So G1 equals graph x, let's see, title, should I give it a title? Title equals, what would this be called? Change in V. X title is going to be equal to x in meters. Y title is going to be equal to V in volts. And then I'm going to do this. Width equals 450. Height equals 200. Otherwise, it just doesn't show very well. Okay, so now I'm going to plot, I'll just say F1x equals G curve. Color equals color dot blue. Label equals x. So I'm going to change this, and I'm going to actually plot them on the same plot. So let's see if it works. Okay, so now what I can do is to say dx equals 0.001. Let's see if that's maybe big enough. And I'm going to say x equals, let's see, so if I want to go around the value of 0.101, I want to change it around that value. Then I need to pick some values. Let's just say, let's make this even smaller. 0.001. I'm going to say this is going to be RTO.x minus 0.01. And then I will say, while x is less than RTO.x plus 0.01. So I need to pick a range over which I'm changing that value. Then the first thing I'm going to do is to say x equals x plus dx, otherwise it would be an infinite loop. And what I want to do is to calculate the potential and plot it. So let's just do that all in one step. F1x dot plot. The x coordinate is going to be x. The y coordinate is going to be v of vector x RTO.y 0. So I'm changing just the x value. I'm not changing the y value. That's why I'm using that RTO.y. I'm going to keep the y value it is. And that should work. Let's save it because you never know. Okay, so there it is. That's pretty good. So this is the point where I want the potential, right there. And so I need to find the slope of that. And I'm just plotting this to show you what it looks like. Let's calculate the slope. And what I'm going to do to calculate the slope is I'm going to move. Let me show you. Let me show you in on the paper what I'm going to do to calculate the slope. So I'm switching back over here to paper. Okay, so suppose I have that data right there. I have my V. I missed something. Okay, so I have this. So here's V, here's X, and I have data like that, and I want to find the slope right there. What I'm going to do is imagine these are actually just finite points. And they're really close together, but they are finite points. So that's where I want to find it. That's my x0. This is going to be, let's call this width delta x. So that point right there is going to be x0 minus x, minus delta x. And this point is going to be x0 plus delta x. So then I can say the partial of v with respect to x is going to be equal to the slope here. So the slope is going to be the change in the vertical, which is going to be v of x0 plus delta x, which I have that function, yay, minus v of x0 minus delta x, and then I need to divide by the width, which is going to be 2 delta x. Okay, so I can go ahead and calculate that function, and then that should be the negative of the electric field at that point. So let's do this in one motion. Okay, so I have that. I have my plot. Let's get some extra lines down here. Okay, so that's that. Now I'm going to calculate, let's say, CEX. That's my calculated electric field. It's going to be equal to negative V of RTO dot X plus dx. It's a vector. I gotta put a vector. Vector. And then I have RTO dot y, RTO dot z, which is 0. That's fine. Minus v of vector, same thing, but I'm gonna say RTO dot x minus dx, RTO dot y, RTO dot z. And you could actually just subtract a vector and do this a different way, but you know, I always think about these things afterwards. So then that is the vector, then divide by 2 times dx. And let's print EX equals CEX, and it should be in volts per, I'll also go to volts per meter, which is the same as Newton per Coulomb. Back up here, I'm fixing this. That does bother me. Let's put this in volts. Okay, now I can also, let's print, just to check, E equals, and that's going to be E RTO. That's using my other function. So I want to see if the x component of my calculation is at least close to the x value from this, which I didn't put there. Okay, if this works, that's a double high five for me. And it didn't. Print unexpected punctuation. E equals RTO. Oh, I got an extra parenthesis in there. That's weird. Again, another error. Missing right parentheses in line 37. Must be up here. Okay, so let's see. So I have parentheses. Okay, you got to look closely. Okay, I'm missing a parenthesis right there, I think, because those two match up, and then this one matches up with that one. So I don't have, I think I need one more right here. Let's try that. That's a lot of parentheses in a row right there. Okay, well, it did something. It did not get the second. Did not get this. Cannot subtract a vector and a scalar. Okay. RTO.x, RTO.y, RTO.z. Oh, no. V of that, V of that. Where did I have the vector? dx, vector, vector. Let's do this. V1 equals V of vector, all that stuff. Oh, no, that's right. Oh, I see what I did. Okay, I'm definitely missing some parentheses. That's fine. So let's just cut this and put it in pieces. One of the nice things about Python is when you have an equation that's too messy, just make it into two equations. So let's say V of that. Okay, so then I can see I match up all my parentheses. That's my left potential. And then I can say V2 equals V of this vector. Yeah. So I have plus and minus. And then, I'm sorry, that's my right one. And then I can say this is going to be equal to, I can just write it out simple. It was a parentheses problem. V1 minus V2, all that divided by that. Okay, I think that should work. I still will get the double high five if it works. No? Can't find variable CE. Oh, CEX. CEX. Oh, CEX. Gosh. Okay. So this first electric field right there, that's the one I calculated before. I don't really need that. But you see, I do get the same, approximately the same thing. It's not the exact same thing because one is an exact calculation. One uses finite element to move the thing back and forth a little bit to calculate it. So they're going to be a little bit different, but they're close enough that I'm pretty happy. So I do get the electric field. Now let's do the same thing for the y direction. So I'm just going to copy this and then go down here and say, do the same thing for the y, while y is less than y RTO.y plus that. And then I need a function up here. F1y equals g curve color equals color dot red label equals y. Okay, so now I need F1y plot v of, this is going to be RTO.x. Remember, this shows you how a partial derivative works. A partial derivative works by not changing the x. So I'm not changing that. I do need to put my y value up here. Y equals RTO.y minus 0.01. There, that's good. And then this is going to be just y. Technically, this should be RTO.z. I'm going to change it up here too. RT, which is 0, but I'm just trying to be a good person here. Okay. So there, and then I need y. This is where you would get destroyed. dy, y, y, and I didn't define dy. dy equals 0.001. Okay, so that will plot the change in potential for that. Oh, else, and I will look at that in a second. And then let me put a dot where I want to find the electric potential. So let's do that too. E dot, I'm just going to call that, equals G dot, color equals color dot green. Let's see if you can even see it. And then down here, I'm going to say E dot plot. Oh, I guess I would need, this is a potential plot. I'm not going to do that. Okay. This is not going to work. Okay, that's fine. Let's run it anyway. Whoa. See right here, I almost made a mistake. Okay. Yeah, that's not going to work because my change, G dot. Okay. G dot. Oh, that's not even a thing. That's fine. Get rid of that and run this. It's going to look weird. Yeah, because see, what my two values are so different. Let's just not plot the x. So I'm going to get rid of the x so we can look at the y. So don't plot that, and I'm just going to plot the y now. And it's vertical. It's vertical. That's weird. That's because I didn't change it. I did f1.plot rt, no, y, rt. No, it should be y right here. Okay. And there you can see how the electric field changes, and we're trying to find the slope of this right here. So now I can do the same thing I did up here. I'm gonna just copy all this. Let's copy all this. Put it down here. And the graph is just for fun. Okay, so now, but up here, I'm going to change this to rto.y. And that's because it's going to be rto.x. And then rto.y plus dy. And this is going to be minus dy. And this is going to be that. And then this is going to be dy. And this is going to be c temporary ey. ey. Let's see if we get it. Okay. Double high five. That was for me and for you for following along. Okay, so here I get the electric field. This electric field right here is calculated by how the potential changes. That's the x component electric field. It agrees with my exact value right there. Close enough. Here is my calculated y value based on the change in y values at that location, and it mostly agrees with the y value of the electric field directly. Okay, so I will include this code down below, and remember, this is a practice in using that divergence, the del of v, to show that it's the same as electric field. That's why I want to do this. There are some cases where it may be super important to do it that way. Maybe you couldn't calculate the electric field, but you could calculate the potential. Then you could still use this method to do that. Okay, so like I said, code down below. If you have any questions, comment down below, and I will try to address them. And that's that.